Hello, and welcome back to the QuadTree project. So this will probably be the very last episode of this series because what we've done in the series so far is we've built out the QuadTree data structure. We've added points to this QuadTree structure, and we've allowed these points to dynamically move. And the movement of those points will automatically update the QuadTree, so that as the points move, they get a lot allocated to the right leaf node in each of the QuadTrees. And if the leaf node is has more points than the critical number of points allowed for that leaf node, it'll subdivide or merge back if the density drops below that critical value. And in the last episode, we also had a option to have a bounds or a rectangle that we wanted to query. And then we basically queried the QuadTree for all of the points that are within that bound. So in this case, as I move my mouse around, I'm moving the red square around, and the QuadTree is querying all of the points within that red square, and that's what you see as the green points inside this animation. So essentially, this allows for a really quick way to search for particles that are within a certain region of interest. This could be in the neighborhood of another particle if you wanted to do particle-particle interactions, for example, or if you wanted to do any sort of grid search where you only wanted particles in a certain location. You could really quickly query the QuadTree, and it'll fetch back the response very, very quickly. And you don't have to do this calculation for all of the particles, since you're spatially dividing the grid with the QuadTree. You can do the very fast, crude search of narrowing the bounds of interest with the QuadTree, and then you only have to do the comparison of the actual of only a small subset of particles. And that's why, as I move things around, things are really, really fast. You see in the background that the frame time is taking about 15 milliseconds to render, but it's mostly because of the actual particle rendering. So if I turn off the particle rendering, you can see that the frame time is almost 1 to 2 milliseconds, and as I move things around, it's not taking up any time at all. Okay, so because of that, we have a very good QuadTree data structure, and we have a good way of updating these particles. So to close out this whole series, I thought we could just spend a little bit of time doing particle interactions, creating a very simple, crude particle collision system, which will leverage the benefits of having the QuadTree. And this will be a very simple example of how to use a QuadTree data structure for doing physics n-body simulations. Okay, so without further ado, let's get started. So right now, what we're doing is we have this main event loop here. So this is while the window is open, this is the SFML window. We have basically this one function that updates the points. We pass in the points and the global bounds, and then this update points function essentially just moves the particle with a given constant velocity. And then if the particle is beyond the bounds, either the left or the right bounds, it reverses the particle velocity along that direction, and then just moves the nudges the particle back into the bounds, so we can accurately add it back into the QuadTree. There's a small epsilon here that basically is a cushion. We're allowing these particles to move like within an epsilon distance outside of the bounds, because we're not sometimes this can happen within a time step. So we're allowing the particle to move beyond that bound, and then we basically move it back in within this epsilon distance from the bounds. So this works pretty well, and what we really need to do now is essentially have a way to calculate particle interactions and update this velocity over here based on some force. And there's lots of forces that we can do. Gravity is always a very common one, but gravity can be a little tricky because it's an attractive force, and so you have to deal with particles colliding or getting too close to each other. So instead, I thought maybe we could do a repulsive force. So we'll treat all of these particles as point charges that are just kind of randomly zipping through space. They all have the same charge. So think of these maybe as electrons or protons. And since they have the same charge, they're going to repel away from each other, and we can model the repulsive force. And basically, it's going to act as very simple sort of collisions. And so since this force is called the Coulomb force. Let me just quickly pull it up and show you what it looks like. So this is known as Coulomb's law, or the Coulomb force, and the force is essentially proportional to the two charges. divided by and inversely proportional to the square of the distance between them. So this is called an inverse square law, because it's a square. It goes as square of the difference of the distance, or the inverse of the square of the distance. And another example is something like the gravitational force, which means that as particles get really far apart, since r goes up to a very large number, the actual force drops to a very small number, which means that we don't actually have to care about interactions between one particle that's maybe on the left and another particle that's way on the right of the screen. We only have to care about particles that are very close to each other within a neighborhood of interaction. And so we can define this neighborhood to be whatever you want, based on how accurately we want to model this force. As we include more and more particles, the approximate force that we're using or that we're calculating will be accurate. And as we use less and less particles, the force itself will become more approximate. But for the sake of the simulation, it should be good enough that we don't have to really deal with it. Um, the value of this neighborhood, how big this neighborhood is going to be, dependent on this coefficient over here, the coefficient of proportionality. Physically, this is known as the electrostatic constant, Ke, and it's a you can get a number that's defined in SI units. It's like 1.6 10 to the minus 9. Oh, sorry, 8 times 10 to the minus 12 or something like that. So we can use that real number, but our distances are in dummy units in our simulation. The charges are going to be in dummy units in our simulation. So we can just say that we're scaling all of these units up by some random number, and this Ke can be some frame parameter that makes everything dimensionally consistent. So we're going to keep this K as a free parameter. We can put dummy values for the charges. It could be just 1 to make life easy. And then we can also set a mass for these particles. We can set the mass to be 1. And in the units where the distances are in whatever units we're working with, the charge has a value of 1. The mass has a value of 1. We can set the Ke to be a free parameter that controls kind of how strongly particles interact in our simulation. Okay, with that said, we just basically need to implement this. So this is for a force between any two particles. But the force is additive. So as you add more and more particles, it's going to basically add up one by one. This is the magnitude of the force. The actual let me see if I can find the there you go. So the actual direction, or the vector of the vector form of the force, is going to be along the distance between the two charges. So if you have two charges between like so, the force is going to be aligned along the distance between them. And as you have more and more charges, you're going to basically add contributions from each of these vectors based on the magnitude of the distance between them. So in this case, we just have to deal with breaking down our forces in terms of the global x and y coordinate system. But as long as we're maintaining the vector form accurately, we should be able to account for that pretty easily. So let's go ahead and really crudely put all of this together in our code. So what we want to do here in our update points is we want to create new values for the acceleration. So we have xy velocity, xy and positions and velocities. So in our point.h, let me just close this because we don't need it. Let's add a acceleration term, like so. And we're going to set all of these accelerations to 0. So let's initially start at 0. So, and the way we want to do this is in our interactions.cpp, we want to update our velocity by this acceleration. So let's really quickly add that in here. Like so, and then the same for our y velocities. So this form of updating, where we're updating the velocity by basically delta time and then updating our points by delta time, or position by delta time, is called Euler's method, because we're doing a single update for the velocity and a single update for the position. And by far, this is the least stable, least accurate method that we have for numerical integration. Because what we're really doing is integrating the velocity with time and integrating the position based on that integrated velocity. There are much more sophisticated numerical integration schemes, but that's way beyond what we're trying to do here. We just want a very crude simulation just to show off the fact that we're able to do large n-body simulations. So for now, this is fine, but just note here that this is called using simple Euler's update. Very inaccurate when the number of time steps becomes large. So we basically accumulate error for each time we do this update, which deviates more and more from the true physics solution if we did an actual accurate integration. So for now, this is fine. But if in the future we come back and we revisit new numerical integration schemes, we can update this as we want. So what we need to do now is we've updated our velocities. Down here, we should set our acceleration to 0 as well. So we basically reset it. And then up here, we need to accumulate the forces on a given particle. So once we accumulate all of the forces, we should be able to, for a given particle, we have the new acceleration. And from that new acceleration, we update the velocity. From the new velocity, we update the position, right? And then we reset the acceleration back to 0. So ideally, we can do it all together. We can do a calculation of the acceleration right here. But remember that the issue here is that our acceleration, if I just pull up our Coulomb's law again, our acceleration depends on the positions between the particles, like so, right here. And so if we update the position of one particle prematurely and use that new position to calculate the force on a new particle, then things are going to be out of sync. So instead, it's actually better to calculate, to basically cache the acceleration for all of the particles at once, and then update the positions of those particles and rinse and repeat globally again for the new time step. So that's what we're going to do. So what we're going to do up here is to actually have a different new for loop, like so. And then here we need to calculate the force on particle I. So the way we need to be a little careful here, because we're looping through all of these points, and ideally what you want to do is for a given particle I, you need to loop over all neighborhood all right, how do we call this, neighborhood point in like the points that are in the neighborhood, and then we add up the force. We calculate force between point I and J, and then add it to point AX and point AY, like so. It's giving me a warning because neighborhood points is not defined, which is fine. So what you really want to do is is for each of the point, you figure out what neighborhood of points you're interested in, get all of those points within that neighborhood, and for each of the points in that neighborhood, you calculate the force between using Coulomb's law, and then you add that force as an acceleration to the points acceleration in the x and the y term. Right, but the issue here is that let's say you're looping through this first list over here. So you're starting with particle 0, right? You calculate the force between particle 0 and particle 1, particle 0, particle 2, particle 0, 3, so on and so forth. What happens next is that when you loop and switch over to particle 1, you're calculating the force between particle 1 and particle 0 all over again, which is wasteful because we've already done the force calculation between particle 0 and particle 1. And remember, by Newton's third law, if you calculate the force between particle 0 and particle 1, the force between particle 1 and particle 0 is just going to be equal and opposite. So you don't have to do this calculation all over again. You just need to do it once, and then just invert the value of the acceleration for the second particle. And so in that case, we actually don't want to loop over all of these points all over again. We want to essentially only loop over all of them once and update the particles only once. So in this case, basically the way we would do it is, let's say we start from the beginning. Let's say we say particle 0. right? We calculate the force between particle 0 and 1, 2, 3, 4, 5, 6. Now, when we go to particle 1, we know that we've already covered all of the particles before particle 1. So we've calculated the force between particle 1 and particle 0. So essentially, we should say we only want to calculate forces between particles when the ID or the index of the first particle is less than the index of the second particle. But in our loop like this, we actually have no idea what those indices are because this neighborhood is coming from our QuadTree, and those particles could be randomly situated. So what we need to do first is to actually add a index parameter to our point. I think this needs C standard library, right? We have an index like so. We add it to our constructor. We initialize it like so, and I know it's going to give us an issue in our main, but now we only need to make sure that if point the ID of the point is greater or equal to the ID of the neighborhood point, like so, then we continue. What this is saying is that, let's say this is point 0 and neighborhood is 0.1. So since 0 is less than 1, we're completely fine. We need to calculate the force. Then we calculate the force. Like so. Let me just move this down. If let's say this is 0.5 and this is neighborhood is 0.0, we've already done the calculation between 0.5 and 0.0 when we did 0.0 here, right? In that case, we don't need to redo this calculation. We exit. So here we'll just say we've already calculated the force between an earlier index and the current index. So we can just skip it. And then when this is not true, when we're calculating the force between a later index and an earlier index, now we want to calculate the force because we haven't looked at these two pairs of points. So now all that's left to do is to actually figure out what this neighborhood points is. And for that, we need the QuadTree, because if you remember, we have a way to query all of the particles within a neighborhood. In this case, the neighborhood is defined by this red box. So here, for this point, we just need to define a neighborhood that we're interested in, where the force will actually be meaningful, and then fetch all the points within that neighborhood. So let's first define that neighborhood. This is going to be essentially some radius around the point of interest. So let's say this is point x minus some neighborhood radius, point y minus some neighborhood radius, and then twice this neighborhood radius. And all this is saying is that we're defining a box that is centered at point x, point y, that has a width of twice this radius that we're interested in, right? And we can define that radius to be as big or as small as we want. Remember that each of these particles had a radius, as we define here. We define that radius to be 0.05 units. So we can just define, an arbitrary distance around each of these points where we know that the point is going to feel some force. So this is going to be a free parameter. So right now I'm just going to define that as a constant value, and then we can come back and revisit it when we have actually set the scale of our simulation accurately. So let's just set this to be maybe 0.5, right? Like so. This is supposed to be bounce, like so. And now we need to pass in our QuadTree, actually, because we need to use our QuadTree to fetch. We need to fetch our QuadTree to get the neighborhood points. like so. And then here, we need to create how do we define it here? Just go up. So for our query points over here, where you use QuadTree.query, we pass in the query bounds that we're interested in, which we've defined here as neighborhood bounds, right? Neighborhood. And so we need to pass in a vector of shared pointers of points. So let's just copy this over. And we can define this in local scope within each of the loops, which is fine. And then this is just going to be neighborhood points, like so. And so here we just need to query our points. There's a pointer. So the quad tree, we're going to query the neighborhood, and we're going to get back all of the points within that neighborhood, right? And this list of neighborhood points is going to already have an ID, so we just need to do this check. Cool. So now we need to actually calculate the force. So just to recap where we are, what we've done is we're looping over every single point. We're creating an arbitrary small neighborhood around that point where we know that if there are points within this neighborhood, then the force between them is going to actually be meaningful and contribute to the true acceleration to some approximation. We're using the quad tree to fetch all of those points within that neighborhood, and for all of those points that are being fetched by the quad tree, we're going to calculate the force between our particle of interest point I and our neighborhood point M, right? So let's just crudely define what the force looks like, and then we'll create magnitudes for it. Okay, so we need a float. We need to calculate the distance. So let's just create the x, the y value, and then let's create a force number. So the x is just going to be point x minus neighborhood point x, like so, and then just repeat that for y. And then the distance is just going to be xx times xx plus yy times yy, like so. We should take the square root of this. I think square root is, yeah, like so. So this gives us the actual distance. And then the force, the actual magnitude of the force, is just going to be some arbitrary k. Let's call this k Coulomb, just to be specific, times we're going to have the charge for these points. We're going to let's put free parameters in here in case we have to come back and change this, over distance times distance. Just to show you why I wrote it this way, let me pull up the definition of the Coulomb force again. So here you go. Let me make this slightly smaller, out of the way. And here you see that the 1/4 pi epsilon naught just collapses into a free parameter k because all of these are constants. The q1, q2 are the charges of each of these 2 points. So point q and then endpoint q, those are q1 and q2, divided by distance squared. So that's the magnitude. This whole parameter is the magnitude, or maybe let me go up to the top. So this whole parameter is the magnitude over here. What we need to do is to add the direction. So in this case, the direction is just the unit vector. Our hat is just the unit vector between point 1 and 2. And now to break our force into that vector form, we just need to convert this into R1 and R2. So let's see what that looks like. So let me bring up a quick scratchpad. So let's say we have our point 1 here, and then we have our point 2 here. Let's just make this a little bigger. And then we have this line. Let me make this a little wider. This out a little bit. And so this is our distance between these 2 points, right? This is point 1. and then this is our point 2, like so. The force of point 2 on point 1 is just going to be along this vector over here, along this r hat, in a direction of our choose. In depending on what the charges are, it's either going to attract, which means 2 being here is going to pull it closer, or since these are the same charges, it's going to push it away, right? So the actual force between them is going to be along the same vector, but pointed in the opposite direction, like so, right? So what we need to do is to break down this force into x and y, which we already have calculated, because this distance is defined by the xx and the yy that we calculated. So this is actually xx, and then this is yy, like so. So if I move this force down here, we can draw a similar triangle, right? So this is going to be the force in the y direction, and then this is going to be the force in the x direction. And since these are similar triangles, right? This is going to be F, the total force over here. This vector is going to be F, which is the total force. This we'll call Fx, which is the Fy, which is the y component of the force. And then this we'll call Fx, which is the x component of the force. Since these are similar triangles, we can actually just equate these two triangles together and say essentially that yy over the distance is the same as Fy over F, like so. Let me just make this bigger. And similarly, xx over the distance is just going to be Fx over F. We'll have to be careful about the signage, depending on which direction things are going. But we can deal with that based on whether the magnitude of the force is positive or negative for one charge for particle 1 versus particle 2. But in terms of the raw magnitude, we can calculate, we have F, we have Yy, we have distance. We can calculate Fy and Fx purely through this similar triangle concept. So let's do that right now. Let me remove this. So we have our force. For visibility, let's just create Fx and Fy. Fx is just going to be xx over d, distance times force. And then Fy is yy over distance times force. So, right? And then our point's acceleration is just going to be equal to Fx over this point's mass. And then the same thing for y, like so. And remember that the Newton's third law, equal and opposite reaction. So the neighborhood's point is just going to be negative of these values. So there are a few things that we need to define here. We need to define the charge. I'm just going to be explicit about it and call it charge. And let's just define these to be constants. So let's say float mass equals 1, charge equals 1. That should fix that. And then we just need to define this k Coulomb, which again, these are free parameters. So right now, let's just say k Coulomb equals 1. Like so. And the reason we can do this, reason we don't need to put in exact numbers, is we're working in arbitrary distance units. And in our artificial world, the value of one charge is of the charge of an electron is 1, the mass of an electron is 1. So in these units where these values are 1 each, we can set this Coulomb parameter to be whatever we want, such that things are consistent. Because again, we're working in artificial units. So now the question is whether this force is actually acting in the direction that we want, and we can do that by quick, simple checks, right? So let's say these two points are these 2 point charges are separated by a distance. The Coulomb force is repulsive for 2 charges of the same magnitude of the same sign. So if this is a positive charge and a positive charge, then the force should be repulsive, which means that what we should have is the two particles moving further apart from each other. So the acceleration should be pointed away from each other in the direction that we're interested in. So since we're calculating, we'll keep the point of reference as the point 1, right? So in this case, if since everything here is positive, this is going to move, since our acceleration is positive, this is going to move our force in the direction of xx and yy. So in this case, let me just pull up our diagram over here. So in this case, point 2 is to the right, so xx is positive, and point 2 is to the further above, so yy is positive. This means that in this case, if we keep the magnitude as it is, the acceleration that point 1 is going to experience is going to be to the top right, because the force is positive in the x and the y direction. So if we want to reverse this, what we really want is for the force to be pointed opposite to the direction of the unit vector. So if we wanted force y to be pointed downwards while y is pointed upwards, we'll just have to invert the magnitude of this force. So in here, we just have to say this is negative, and now we have the force being the force on particle 1 being opposite in direction to the vector connecting the two charges. And since we've already defined it up here, the neighborhood point is going to feel exactly the opposite force, and that is also completely fine. So everything would just kind of work out. So in this case, we've actually defined all of our all of our forces. Just to be really clear on what we've done so far, we've looped through all of our points. We've searched for a arbitrary neighborhood around these points based on some arbitrary distance that we defined here. For all of the points within that neighborhood, we've calculated the force through the Coulomb force. And what we've done is updated the acceleration based on this. Now, there's a few points that's going to affect things here. Firstly, if the distance goes to 0, our points are going to blow up. So what we should do is to add a very, very small value here so that things don't blow up. The second thing is that we should make sure that we're resetting our acceleration to 0 at the end, and we've done that. So this should be complete. What we need to do is to go back in here and make sure that we're passing in. Firstly, we need to pass in the ID over here, like so. In our second case, we're actually creating new points as we click. I don't think we need this anymore. I'm just going to comment this out. And then here, when we update the points, we need to pass in the QuadTree. And so this should work, ideally. What we need to do now is to actually make sure that these values are consistent, but we wouldn't know until we run it. We could do some quick checks, but let's try it out. Let's see what happens. And then we'll see if we need to update these parameters. Most likely our value of the Coulomb force is too high. And so we'll probably have to reduce those by an order of magnitude, but let's just see things blow up right now, and then we'll come back and adjust them. So it compiled without a warning, which is great. So let's see initially if something happens. So I'm going to start the simulation. Oh, things are very sluggish and something happened. There was a seg fault. I wonder why. That is a little strange. Let's run this with Valgrind to see where exactly the segmentation fault is happening. So Valgrind is a good debugger. It's going to take much longer to actually render, but let's just press play. Let's see where it actually crashes. We should do this with less particles so that things actually work quickly. Yeah, let me do that. Let me rerun this with less particles. Oh, 10,000 particles. So let's do 100. Okay, that's really good. So let's run this out. Oh, that seems to be working. So I'm not sure what the issue was. You can see that the particles are actually repelling from each other. So what I'm going to do is let's clear this. What I'm going to do is to reduce the frame rate here. I'm going to limit this to 10 FPS so we can actually see things crawl one by one. And I'm going to also reduce the delta time. So let's render this again. Oh, sorry, compile this again. I'm going to run this just as it is. I'm going to turn off the QuadTree display, and then you can just see. There you go. You can see that the particles are actually bouncing away from each other. Um, I'm trying to find a good example of two particles that are. So those should be moving apart, but they're not for some reason. Oh, they got really close and they got pushed apart. So I think actually the Coulomb force is actually too small. Um, or maybe 0.5 is too small. Let's bump this up. Let's set a value of 10 for this. And then rather than having a random normal distribution here, I'm going to set this to be a uniform distribution. This is for the position. And let's just distribute this between 5 and 20. So our domain is between 0 and 25. So we're just going to randomly distribute our points between 5 and 25 so that we're not, when we do a normal distribution, we're really squishing a lot of particles at the center, which is why we have this explosive kind of disruptive event that's happening at the beginning. Let's have it the simulation be a little more organic. Okay, so I have these particles. And you can see that they're slowly moving apart from each other. I think maybe the force calculation might be incorrect because I don't see these two particles really pushing apart from each other, or the neighborhood calculation is incorrect here. Is this correct? If the point ID is greater than the neighborhood point ID, we should continue. Uh, I think that's correct. What it might be is that it's just that the number of points that we are using here, the radius here is just too small. So let me set this to be slightly bigger. Let's set this to maybe 1. We're still not seeing two particles really move fast enough away from each other. Maybe I'm updating these things incorrectly. Did I miss an fx or an fy somewhere here? So let's put some debug statements. Like so, and then down here, let's also print out the force, or sorry, the acceleration. And then here, let's just exit out, just so that we see what that initial acceleration looks like. Okay, so our first point has 2, and our acceleration is fairly high. So if the neighborhood point is just 1, that usually means itself. So that's being ignored here, which means that 0.5 only has 1 point in its neighborhood, which is itself. So that's fine. We don't care about that. We might just need a few more points. So let's bump it up to maybe 1,000, and then see if things are working a little better. I need to turn off these print statements and then remove the exit. I am resetting it to 0, which is great. That's correct. So they are scattering correctly. So what you'd expect from this force is that initially, when the particles are all bunched up together, they should scatter. But what I would like to see is, as these points move closer, they should be bouncing further away from each other, which I'm not necessarily seeing. But then again, the simulation is moving too quickly. So let's just set this to 2 points, and then let's increase the radius to like 15. And let's see if these 2 points are actually bouncing away from each other. So there they are. There's the 2 points. So initially, these 2 points are moving closer together. I think not necessarily. Let's run that again. No, I think the time step is a little slow. Let's bump it up. Let's set this frame rate limit back to 60. Let's bump this up to like 0.02. Okay. They're moving closer together. So they are bouncing apart from each other, but the collision happens at a very small distance, and as you can see, it actually like picked up a lot of energy, so it's not actually conservative. So there is a problem with the way that we've defined this force. What we could do is to plot also the acceleration of each of these particles to see if they're actually moving away from each other. But let's bump our Coulomb force up to maybe 100 and see if that makes a difference. Oh, I see. So they're actually bouncing incorrectly. So there might be a problem with the way that we've defined this force. Both of these points should have charge of 1, so that's correct. I mean, these should be endpoint mass, but that's fine. I wonder if I made a mistake in the force calculation. Let's go back to the whiteboard. Um, so the force on point 1, based on point 2, should push it to the bottom right. The force on point 2, based on point 1, should be pushing it to the top right. So the magnitude of the force is just going to be. Oh, I see. Okay, I did make a mistake. So my convention is wrong. So my point x, my x-axis is actually negative in this case. My x-axis is actually pointing in this direction. So either I should flip this, I should put endpoint x minus point x, or I should remove this negative sign. So let me remove this negative sign and let's see what happens. The issue is that my radial vector was pointing already towards the center of point 1, whereas my drawing was pointing towards the center of point 2. So let's run this. There you go. So they're actually moving further away from each other. Let's see if they get closer. There you go. So they're actually drifting further apart from each other. So that's correct. And I think the Coulomb force is a little high. So let's set it to 1, maybe, and we don't need as high of an interaction radius. We just need something like 1. Let's bump up to 500. Let's see how this works. So we have this many points. Oh, there you go. Perfect. That's actually exactly how it should work. So these points are being, you can see that they collided, they got very close to each other, and they kind of bumped each other away. So the issue here is that, as you can see, the speed of these particles is going up. But the Coulomb force is a conservative force, which means that it actually doesn't as these particles, as you've added a system of particles, the total energy of that system shouldn't actually go up. But clearly here, the energy is going up, and this is because of a bunch of numerical mistakes that were made in our simulation, including the fact that our numerical integration scheme is very, very weak. So what we can do, the way we can mitigate this is actually reduce the time step that we have here to something a little smaller. Actually, let me set it to 0.01, and then I'll reduce the Coulomb force even more, like so. And this should allow us to capture those really close encounters more accurately. Let's do this. And as you see here, things are actually like the particles are moving away from each other, but they're doing it at a much more reasonable and moderate pace. And if you look at our QuadTree is also going to update in real time based on how these particles are moving. So the simulation itself is really, really slow right now, which is fine, because it's as we decrease the time step, we're capturing these interactions much more accurately. And if we wanted a higher time step with more accuracy, we would need to update our numerical integration scheme or the way that we're calculating these interactions. But you can see that two particles are coming close together, and they're actually bumping next to each other, and they're going further apart. And this is exactly how you'd expect particles to behave. As they come closer, the repulsive force between them drives them further apart. So let me just let the simulation run. I'll turn off the the grid for a little bit. We can just watch the simulation run to see if things are working correctly. And here you see that there is interactions happening. So here there's interactions happening. As they get closer together, they actually like slow down and then they get pushed apart, which is exactly the way we want. Okay, now let's go crazy. Let's try to increase the number of particles that we have from, let's say, 500 up to like 10,000. And just to make sure, I think the capacity is fine. Let's just run a quick experiment. So actually, I don't think my... Let me move this up here. So now we're actually measuring the total clock time of doing these particle updates, which, remember, does all of these particle interactions. So that our frame time here should tell us how long it's taking to do these calculations. So with 5,000 particles, it's taking about... Oh, we haven't started the simulation, so let me run it. And it's taking about 300 microseconds or milliseconds per frame to calculate all of these interactions. Right? And if you look at our QuadTree structure, it's pretty well subdivided. Now, what I'm going to do is to actually decrease the number of the capacity of the QuadTree, so we get more finer subdivisions within our QuadTree. So let me render this again, and we'll see how the frame rate changes. So it hasn't changed too much, mostly because it's probably a uniform distribution. But you can see that the QuadTree itself has much more finer structure here. And as these particles spread apart, you'll see that the performance actually increases. There you go. We were actually dropped down to 300 milliseconds compared to where we were before. We were at 360 milliseconds, and we've dropped even further. This is because as you increase the granularity of the QuadTree, you're basically improving the efficiency of this spatial data structure, because you're allowing for the QuadTree to tell you more quickly whether a region of interest that you're defining has the particles that you're interested in or not, right? So if you make your QuadTree more and more granular, it holds less particles, and so it's much more efficiently able to discount particles which are not within your region or bounds of interest. As you make your QuadTree hold a higher capacity, that means it's going to do more and more actual checks against particles within that leaf node, which makes it less efficient. And you can one other thing we can try to do is we set so right now our simulation is running pretty uniformly at 240 milliseconds. If I decrease this radius of interaction, let's say I drop it down to 0.5, right? Let's see what that does to our frame time. You see it dropped it by basically half. And this means that one, it's actually doing less, it's requiring less particles to actually interact with each other, which means that the actual individual particle interactions are taking less time, right? And I'll drop down to almost 100 milliseconds. This is at the cost of a more accurate, of a less accurate force, right? Because we're including less particles to calculate our force. And so our force calculation itself is a little less accurate, but the speed of our simulation is much faster. And we can make this a little better as well. We can actually do a little bit of optimization, because we haven't been using any sort of optimization in our compiling. So here, as I'm compiling this, I can also add in O2 or O3, which is second and third order optimization. And if I run the same thing again, you can see that we're now running crisp and smooth 30 frames per second. And this has done absolutely nothing in our actual simulation, but what it's done under the hood is the compilers understood that we're calling a bunch of instructions over and over again. So it's optimized those instructions so that it's doing them all at once and then caching the result rather than having to calculate thousands of interactions. This is just the very last level of optimization that we're able to eke out of our simulation. But if again here the point still stands. So if I take this third level optimization and I increase this, if I say this should be like 15, right, which basically means that we're including all of the particles. Our entire domain is between 0 to 25. So if you set a radius of 15, that means that every particle is now being checked against every other particle. So we're not actually getting any sort of optimization from our QuadTree data structure. And even with the third order optimization in our compiler, our simulation is crawling at 1.6 seconds per iteration. But you'll see that the force, if you look at the actual force calculation, you would see that including these forces from particles that are really far away will not actually contribute meaningfully to the accuracy of your simulation. So you're not actually getting a lot of benefit from doing these particle simulations with such fidelity. You're getting basically very close to the same sort of performance if you reduce the number of particles in your simulation. Let's say we'll drop back to like 0.25 or something. You're still able to pretty accurately render your simulation, your n-body simulation, while still maintaining really good performance in your simulation. So with all said and done, this is kind of the benefit of the QuadTree. So let me just render the actual QuadTree. I'm going to remove the particles. You can see how as the particles are moving around, the QuadTree is dynamically updating. And the fact that these updates are so blazingly fast and we're able to query particles within this QuadTree structure really, really quickly allows us to run these sort of very large 10,000 particle simulations in under 10 milliseconds. So with that said, this is basically going to be the end of this series. We'll try to tackle other interesting physics challenges later on through other series. But for now, I'm just going to restart the simulation. I'm going to set it to a really high particle count. Maybe I'll bring back the normal distribution like so. Let's increase the size of our window. Let's set it to 50,000 particles. And I'm going to render these as slightly smaller spheres so that it's not annoying. Okay, and with that, enjoy the particle simulation, and I'll see you in the next video. Bye-bye.